In previous lecture, we studied for the Boltzmann equation, and here from now on, we are talk about the Boltzmann equation of the electromagnetic field. And the title, when you calculate the Boltzmann transport on the field, and we can think that the magnetic resistance. Magnetic resistance and Kohler rule. Yeah, and we know that in previous lecture on the in a blowhole crystal on the magnetic field, the force, the equation of motion can be governed by the Lorentz force cross H, and the diffusion. In this case, the Boltzmann distribution function, the diffusion term. The diffusion term of this Boltzmann equation is that Fk dot diffusion is that minus V dot partial Fk partial R, and in the external force term, external fields term is that Fk dot field is that minus E over H bar E plus 1 over C Vk cross H. That's partial Fk partial K. Yeah, this is a field term. And the summation of this diffusion and the field term is the scattering. Then here we can think that here it is energy. Let's define that. Let's consider the electromagnetic field. Here, let's consider the first term and the second term. And the first term is like that minus U over H bar E dot partial Fk partial K is that anyway, let's define that this minus E over H bar and E times partial Fk partial epsilon K and partial epsilon K partial K. Then this energy is that H bar square K square in the free particles, and here the epsilon dk is that H bar square K. Then mv is that H bar K, therefore it is that H bar K is that H bar K is mv, therefore H bar v. And here is that minus U H bar E dot H bar v and partial Fk partial epsilon K. Then it is that minus E dot V partial Fk partial epsilon K. It is the energy derivative. And because the this distribution function is the Fermi-Dirac distribution function, and anyway, it depends on the energy, because in the Fermi-Dirac distribution function contains the energy term. Therefore, it is more easily calculated by the derivative with the energy rather than the position. And here, in the case of second term is the magnetic field case. It is that second term is that time derivative of the magnetic field is that minus E over H bar C and V cross H dot partial Fk partial K. Then basically, and we saw that in previous case, and basically, if this f function is equilibrium state in a steady state, and basically we know that this partial Fk partial K can be write down this one, and therefore it is that, and therefore we can see that when we use this and V cross H dot V partial Fk partial epsilon K, then it is perpendicular to the V, and the dot product with V, and it is cancel with each other. Therefore, then we can say that if the distribution function has the equilibrium state, and it is equal to 0, then here it is natural, because when you think about that in a sample, and here we apply the magnetic field in the outside direction, then the electrons flows, then electron deflected in this region, and therefore it is a minus charge accumulated, and the plus charge plus image charge can be formed in the opposite side. Then in here there will be generating the internal off diagonal electric field. We call it is a whole electric field. Then basically this charge accumulation, at first it is a non-equilibrium state, but in some time, and the charge accumulation becomes stable. It becomes stable. It generates a stable electric field with a voltage difference. Therefore, the at finite time later, the equilibrium state does not take they do not contribute to the transport properties, and the case is 0. Then in this case, it comes from that dispersion relation is that these kinds of free particles. But when we think about the ion interaction or the interactions or the strong correlation, then there is not this kind of quadratic dependence, moment, energy and momentum dependence. Then in some cases it can be nonlinear term, or the other can another possibility can be considered. Therefore, we should take into account that the distribution function has two parts. One is that the distribution function, one is the equilibrium distribution function, or the non-equilibrium distribution function. Here Fk0 is the equilibrium distribution function, and Gk is that non-equilibrium distribution function. Therefore, this Boltzmann equation, the equilibrium distribution function do not contribute to the transport properties. Therefore, the Boltzmann equation on the magnetic field becomes minus Fk dot for scattering is the minus E dot V. It is a diffusion, the Fk0 and the partial epsilon K. But in the diffusion case, is that equilibrium state can be considered. But in magnetic field term, only It is not, I'm sorry, it is not diffusion. The first term is the electric field term, and the second term is magnetic field term. Magnetic field term is the V cross H, and do not consider for the equilibrium distribution function, but the non-equilibrium distribution function. Okay, then when it is a real Boltzmann equation, but as I said, this f function, distribution function, is a Fermi direct distribution function, basically, but we do not know that the scattering, time rate of scattering, and also this non-equilibrium distribution function, because it depends on the case by case. But it is very difficult to calculate this Boltzmann equation. How to solve this equation? Therefore, we should employ the basic assumption. Basic and the simple assumption is that the relaxation time approximation. Relaxation time approximation is that fk dot for scattering is that minus non-equilibrium distribution function divided by the tau. Then it is the physical meaning of this one is that the time derivative of the field distribution function is equal to the time derivative of scattering distribution function. But here, the time derivative, we do not know that the exact time derivative, but we assume that the time interval of the scattering we set by the tau in some cases. Then tau value can be comparable from the experiment, can be extracted from the experiment. And therefore, the ratio of the dynamic distribution function with relaxation time equal to the time derivative of field distribution function. Here, basically, and this one also, it is a momentum derivative. Momentum derivative is the crystal momentum, but in relaxation time approximation is basically, it is ballistic scattering. And also here, when you think about the scattering centers and the electron scatters and the time t1, t2, but average time for the scattering is that we can denote that it is a relaxation time tau, the average time for the scattering. Therefore, it is the time can be fixed for the average value. It is kind of the mean field theory. And here, and therefore, when we assume that it is that also, and the moment rather than momentum, in quantum mechanical point of view, or the distribution function case, and we can think about the momentum. But in classical mechanics, and the velocity can be easily defined because it is in the particle distribution function. The velocity cannot be exactly defined, but in the ballistic scattering, the velocity can be exactly defined. And therefore, here, velocity is that velocity is the can be write down is the tau and mean prepass. Here, when you substitute this Boltzmann equation and also this term and the scattering can be write down this one, and therefore when we summarize, minus e dot v partial fk 0 partial epsilon k is that 1 over tau plus e of ch bar v cross h, and the second term, because this dynamical distribution function, non-equilibrium distribution function, is the function of velocity. Therefore, the derivative should change by the velocity, like this, in the partial v and the gv. Then, even though we do not the exact functional form of the g, but the gv has a function that minus tau e dot v partial fk0 partial epsilon k and 1 plus tau e over ch bar v cross h in partial v partial k and partial v. Then here this energy derivative can be calculated, and also this magnetic field is given, and the v, it depends on the v, it depends on the v. Then this v also can be v velocity also can be write down as the mean pre-pass divided by the relaxation time. Therefore, velocity v can be think about that it is a function of relaxation time tau. Therefore, anyway, it should have the functional form of the magnetic field in tau. Then tau is that relaxation time for scattering, and it is inversely proportional to the rho zero. Rho zero means that zero field electrical resistivity, and therefore it is that this kind of non-distribution function, it can be write down. It is magnetic resistance, and here is magnetic resistance has a functional form like this. We call it as a Coulom's rule. Coulom's rule can be interpreted like this, and this one shows that in the x-axis is temperature, and the vertical axis is electrical resistivity in some sample on the various magnetic fields. But when you apply, you depict that in the x direction is the h of rho zero, and the vertical direction is magnetic resistance. They may have the single curve. All the data coincides in a single curve. We call it as a Coulom's rule. Basically, Coulom's rule in a metallic system, the magnetic resistance is only a functional form, and the Coulom's rule means that it applies in a metallic system. The magnetic resistance can be defined by that applying magnetic field and zero resistivity, and here times 100%. The unit is percent, and it is magnetic resistance is functional, and a functional form of h over rho zero. It is Coulom's law. The rho zero is the electrical resistivity at zero field, and it is a function depending on the geometric configuration of the metal. And therefore, when we depict that here in the x-axis h over rho zero and the y-axis magnetic resistance, then they may have the functional form. In some cases, if there is a temperature measurements, and some cases, for example, it is 300 Kelvin data, and also other temperature data may have this different this value For example, it is one example. It is one example. And anyway, this kind of data may have the like this any functional form coincide in a single curve. Anyway, it is a red one is the, for example, it is 100 Kelvin, for example, and we already presented the experimental data of the Coller's rule. And here Coller's rule says that in general cases, positive magnetic resistance in metallic system, and there is a positive magnetic resistance in general metallic system. It is reasonable because here in a sample, when you apply magnetic field, and because of the charge accumulation and transport, the number of charge depleted because of the accumulation of charge at the edges, and the contribution to the transport of carriers decreases. Therefore, when you apply magnetic field, the larger number of particles accumulated at the surface, therefore the decreased number of particles to transport electrons. And therefore, positive magnetic resistance is general phenomena in a metallic system. But in some cases, we saw that there is a negative magnetic resistance. Negative magnetic resistance is exceptional because in some magnetic materials, or the correlated system, they may have the very complicated interactions, and the interactions makes that enhances correlation on the magnetic field. Then it can decrease the electrical resistivity by applying magnetic field. Then it gives rise to the negative magnetic resistance. Therefore, when we observe the negative magnetic resistance in a simple metallic system without magnetic elements, and it is very surprising. Then we should understand the physical mechanism why the negative magnetic resistance originates on this case. Therefore, recently, the Fire-same metallic state with the chiral anomaly, chiral current. Chiral current gives rise to the negative magnetic resistance, but to understand the Fire-same metallic state and chiral current, it is very difficult to understand. It takes much time to be studied. Therefore, we do not mention this Fire-same metallic state. But anyway, and when you observe the negative magnetic resistance, and we should consider further in detail.